questions during the talk?
Oh, not at all. I'm sure there are going to be many. Just for curiosity, like, has anyone ever said no to that?
Sorry?
Has anyone ever said no to that?
I don't know. So, well, in the past, not here, but in the past.
Oh yeah, in other places I can imagine, but yeah.
Sometimes it matters the system.
Yeah.
So
Okay.
if you feel like you prefer them,
How flexible are you on the time?
very,
Very, right?
Yeah.
Okay, yeah. So then it's fine.
right on. You can use this table method. Board in middle. Is that okay? Or
I
if
don't.
it is so, we can bring the board.
Yeah, I don't think it'll be needed, so it's fine.
Sure. It is all a short.
Okay. It's good to see you.
Hello, everybody. Welcome to the first of the 2 string seminars this week at ICTS. We're very happy to have Pratik talking about modular flow and gravity. I'm told that the table microphones work, but they're predominantly meant for the Zoom audience. So if you speak loudly and use the table microphones, it should be a win-win. Oh, I should speak louder? Okay. I'm very happy to have Pratik today. That's the most important information. All yours, Pratik.
Thank you so much. So firstly, thanks a lot for the invitation to come here and give a talk. It's my first visit to ICTS and I find it pretty amazing. So I look forward to the few days I'm here. So I'd like to tell you about some work that I've been doing on this topic of modular flow in holography, primarily based on some work in progress with my collaborators at Santa Barbara, Zhidong and Don Marolf, but also based on these previous papers, whose ideas eventually led to the stuff that I'm going to talk about here. Okay. All right, so let me get started by just introducing the idea of modular flow. Hopefully this is familiar to some of you, but if it's not. So in quantum mechanics, let's say I hand you a density matrix rho. The modular Hamiltonian is defined by minus log rho. So this is a natural quantity which appears in a lot of discussions of quantum information theory. It's the if rho was a thermal density matrix, then this modular Hamiltonian would literally be the Hamiltonian of the system. This is some sort of generalization of that for arbitrary density matrices. Modular flow, a caveat here is I'll be talking about one-sided modular flow. Acting on a state is of the following form. It's a flow where the state psi as a function of lambda, which is the flow parameter, is defined by e to the minus I k lambda acting on psi, on some initial state psi. And in general, these states psi and k, which is associated with rho, can be completely independent and chosen differently. I will mention that my results will hold for certain choices of rho and psi, which are related to each other, but more generally, modular flow can be defined for arbitrary states. Right? So why care about this? So in the last decade or so, these ideas have proved pretty useful for a variety of things. Firstly, just independent of gravity, there's been energy conditions in quantum field theory that have been proved, such as the average null energy condition and the quantum null energy condition, and other such insights into quantum field theory, which have heavily used ideas of modular flow. So the proofs of these statements required modular flow. So it's been useful for certain things, and sometimes it takes a simple form. So sometimes, for example, if you have a thermal state, then as I said before, the modular Hamiltonian is just the Hamiltonian. So the modular flow is just time translation. So it's a simple thing. Similarly, for a vacuum state, for the vacuum state, if you just pick half space as your subregion, then this is just the boost operator. And those are some special cases where we understand what this modular Hamiltonian does, but more in more general situations, we don't really understand because it's typically a very non-local operator and it's hard to keep control of it. So that's where holography comes in. And so let me just review just general idea of holography, hopefully familiar to this audience, which is in the context of ADS CFT, is just the statement that quantum gravity in d+1 dimensional ADS is equal to CFT in d dimensions living on the boundary. In particular, using ideas from quantum information theory, people have argued that there's ADS CFT satisfies the property of subregion duality, which is the statement that if I hand you a boundary subregion, capital R, then it contains all the information you need about the bulk in the region little r, which is this shaded green region. And this little r is defined by the region which is between capital R and the Ryu-Takenagi surface, which I've labeled gamma r, which is just the extremal surface anchored to the endpoints of capital R. Okay, so good. Now, in the context of holography, Holography typically simplifies a lot of complicated notions. So entanglement entropy is usually a complicated thing to compute in general, but an area in gravity is a much simpler thing to compute. So in the same spirit, we were motivated to understand modular flow in this context, which is, again, a complicated thing in general quantum field theories, but maybe holography simplifies it, and that's sort of going to be the story for today. Independently of this, in the context of holography, people have discussed modular flow for a variety of reasons. So there was this paper by Faulkner and Lukowitz, which wrote down an explicit reconstruction formula. So if I give you an operator in the bulk, and you want to find out what its boundary representation is, then modular flow played an important role in this map, which takes a bulk operator to a boundary operator. So it was useful in this context. More recently, these authors have tried to argue that the physics of an observer in the bulk can be also understood in terms of modular flow. In particular, the proper time that's observed by observers in certain limits can be approximated well by a kind of modular flow on the boundary side. So it's been useful in other contexts, in holography. Okay, so in holography, in order to understand modular flow, let me first review some results that are slightly older. In particular,
Hi,
oh, sorry. Yeah.
sorry. Yeah, can I ask a quick question, maybe, just to be on the same page?
Yeah.
So in your first slide, you said, psi and Kero could be coming from different states.
Yes.
So if they're different states, is there like a physical interpretation? It's like some you had some psi state, and then you are acting with some excitation or something corresponding to the row density matrix of another state. Is it something?
Yeah,
like
I mean, I guess one situation where you could think about it is like if you started with the vacuum of some Hamiltonian, or like the thermal state of some Hamiltonian, and then evolved with a different Hamiltonian. This is sort of a generalization of that process. So that would be some situation where you say suddenly change the Hamiltonian and time translate with a different Hamiltonian, something like that.
I see. Okay, thank you.
All right. So getting back to ADS-CFT, I'd like to review what's called the JLMS formula. This is a result from 2015 by the authors Jaffris, Lukowitz, Maldacena, and Su. And their result was to understand relative entropy, which is this quantity, which is some measure of distinguishability between two density matrices, rho and sigma, which is defined as trace rho log rho minus trace rho log sigma. And their result was, the way they phrased their result was the fact that the boundary relative entropy computed on this region capital R is the same up to small corrections to the bulk relative entropy in this blue region little r, which is the entanglement wedge or the region that's bounded between the extremal surface and capital R, that by subregion duality is just dual to the boundary state. And in fact, this was the first step in trying to prove something like subregion duality. This was the first motivation for understanding that these regions are dual to each other in some sense. So if a state is distinguishable in this region, it's also distinguishable on the boundary, right? Okay, so that's one way to phrase their result. But in fact, there's another way to think about their result, which is what I call JLMS version 2, which is an operator statement. So really what they did was they started with the Ryutakianagi formula with quantum corrections and considered state perturbation. So you can apply the Ryutakianagi formula to one state and then also consider perturbations, perturbing the state and then looking at the Ryutakianagi formula for that state. When you do that, what you end up with is the following statement. So here K is just the modular Hamiltonian as I defined. So the left side is a boundary operator. It's the modular Hamiltonian reduced for the density matrix. That's the reduced density matrix on this boundary region capital R. And then there are these additional projectors. So the way to think about this is holography is mapping if we pick a subspace of states which have some nice semi-classical description, that maps to some subspace of the boundary theory, right? There's some map which is relating these two. Now, this is not necessarily the full class of states. These are just the nice semi-classical states. So it's some subspace. And so this PC is a projector onto that particular subspace, which is often called the code subspace in this language. So it's projecting onto what you can think of as the low energy effective field theory Hilbert space, but now encoded on the boundary side. This operator, which you can think of as some projected version of the modular Hamiltonian, is equal to A over 4G, which is A here is the area. This I'm interpreting as an operator which evaluates the area of the extremal surface gamma r, plus the modular Hamiltonian of this blue region little r. Okay, that's a more useful version of their formula for our purposes. Okay, good. So this result of JLMS was very useful in the context of holography. People, yeah, sorry, yeah.
Can just go back?
Yes.
So this last operator statement also has order G Newton corrections.
It does, yeah. This is all up to order G Newton corrections. That's right.
And either of these statements is ignoring the dynamics of gravity or including the.
I mean, yeah, good. So there is some subtlety about the calculation of graviton, entanglement entropy, and so on. I don't think there's been a very clear demonstration of the fact, but people often believe that this could be generalized to include those corrections as well. I mean, in principle, we should be including those corrections if we understand how to compute them correctly. So at the formal level, the answer is yes, but there's no like explicit demonstration of this fact. But in some sense, like we're going to interpret this as an operator. So fluctuations of the area are included in the statement when I want to think about this, but at a pretty formal level at this point. Yeah.
So this is what I'm trying to understand. For example, there are fluctuations which, if I just send a particle,
yeah,
or if I have a black hole, and
yeah,
okay, do some gravitational experiment in the
yeah,
that will change the hat.
Yes.
But that would also be some G Newton times something.
Yes.
That effect. So am I supposed to think that those things are included?
So those things would be included, and even after accounting for those things, a statement of this form is going to be true, as I'll explain. But there's still going to be order G Newton corrections to this statement. So let's say even if we include fluctuations, so in particular, like just to preempt some of the things, we will include, like, for example, even different classical backgrounds. So even like non-perturbatively different backgrounds. So in that sense, A is an operator which will just go to that particular background and evaluate what the area is in that particular background. And then you can add order G Newton corrections. I mean, that's just the leading free graviton approximation. We'll not look at higher orders because the FLM formula itself, this formula itself will fail there and there'll be corrections to the statement. But we'll always be working just to this order 1 approximation. So we'll ignore all of that. But there will be, this code subspace that we'll build will consist of different values of the area.
I mean, one reason is that it's not just a technical question. It's not even clear, for example, once you take into account Hamiltonian constraint, what do these objects even mean? Like, say, K hat.
It might all work in this, because in this context, so usually I worry a lot about in this particular case, it might work nicely because if we press everything that you are, then size capacity. If I do something similar for some that region is a part of the gravity. This region is probably which would be the correct state for this. Press all operators inside that are press all operators in the region.
Yes, yes. Yes. But when you say this, yeah, yeah, yeah. Yeah, so at order 1. So at this order it'll match, and then at higher orders you have to account for things like quantum extremality and so on. So that's what I presumed this question.
I was just trying to understand. So you think that the thing defines this k hat?
I don't think in any of these formulas we have that.
Yeah. Yes, yes.
I understand the k hat r, the left hand side is right. This k hat in the right hand side.
Is also defined by pressing degree.
Yeah. That's right. Yeah, I will get to that. So that's right. So the story in gravity usually is that the divergences in A/4G cancel with the divergences in K. For a lot of what I'm going to say, we will assume that we're imposing some sort of a UV cutoff, which sets a scale. So typically the story is this whole sum is renormalization group invariant. And by changing the renormalization group scale, you can move terms from one to the other. I'm going to assume that we fix one such scale for certain things that I'll say. I'm going to assume that we fix one such scale, and then either of these are well defined. But yeah, that's an important caveat.
But this will assume that the UV cutoffs are the same.
Yeah, that's true. So okay, good. So on the bulk, it's pretty clear what a UV cutoff would mean. What the boundary dual of that UV cutoff is not so clear. So I'm assuming that some such prescription can be made such that we're mapping that to the boundary and then applying the same regularization on the boundary side. Now,
so the bulk,
yeah.
Then the first term is the string scale.
Right? Yeah, something below the string scale. Yeah.
Is it clear to the second term? K hat, right? That's also normalized. That UV effective UV cutoff will be the same scale.
Well,
there are some metrics for results which suggest that it is a dance.
Oh, I was going to say that we can choose to define this theory with a scale which is even parametrically lower than the string scale if we like. That's where all of this is under control. But maybe you're asking about a preferred scale in some sense. Maybe I didn't understand.
That, I mean, it's first
yeah.
Is really a finite because in string theory it will be G Newton is never scale, renormalized.
Not renormalized infinitely, yes. Yeah. But it's scale dependent that
it's scale dependent after scale.
Yes.
But the second term, it's not quite clear that it gets renormalized in this case.
Is that right? I thought there was evidence that. So if that was true, then I mean, what we believe to be true is that this sum is renormalization scale invariant, right?
Up to the scale.
Oh, I see. You're questioning that. Okay, I'm going to assume that we're working at a scale below the string scale. I hadn't appreciated this subtlety before. Maybe we can talk about this offline. But I'm anyway going to assume that I'm going to ignore a lot of stringy correction and stuff. So let's say we're far below the string scale and it's a UV cutoff where A/4G is like some finite thing and this is like well defined. It's just some quantum field theory thing. Yes, that's true. So this is correct. But for certain things, so a lot of my results are going to be for single-sided flow. And you might worry that it's more singular than double-sided flow, but you can still, in the end, I'm going to give you some evidence from, there's other ways of regularizing, apart from two-sided modular flow, there's other ways of regularizing this one-sided modular flow. And we'll see evidence that what I'm going to say about one-sided modular flow is correct in some distributional sense, even though it's singular. And so it's still going to be nice, not too badly behaved. Yeah. Yes.
I mean, you have to assume that the effective UV cutoff
is
even below the inverse radius of radius.
I don't think so.
Because the usual is construction of quantum error correction, what's
Yeah.
that level?
Okay, good. So that's, I guess what you're saying is like the tensor networks are usually on that AD scale. Good. All of these results, so tensor networks are a natural place where all of these results hold, but these results are sort of independent of tensor networks. So all they need is there's some formal map from the bulk to the boundary, which doesn't need to be anything like a tensor network. Which we believe, I mean, it's just ADS-CFT, right? We just believe there's some global map that exists. And the Ryu-Takenagi plus FLM formula holds, which we also believe. And the ADS scale doesn't play any role in these statements. Just those things are sufficient to prove something like this. So I don't need to rely on any tensor networks for this. Yeah. Okay. Okay, good. So this is sort of what we understand about the modular Hamiltonian in holography. Just as a side point, like this is a very important result because the JLMS formula, it was shown in these papers just based on formal arguments that holography can be thought of as an error correcting code in the sense that there's some representation of operators in this blue region on the boundary as some complicated operator which I've labeled as O capital R. This statement, of which is what we mean by subregion duality, is in one-to-one correspondence with both the RT formula plus FLM corrections and the JLMS formula, as I stated in the previous version. And this is actually true for an arbitrary error correcting code. So it's sort of more general than ADS-CFT, but in the context of ADS-CFT, it's like naturally interpreted as this bulk statement. So this was true for exact error correcting codes, and exact error correcting codes would sort of miss the sort of corrections that you were pointing out. Like, for example, the RT plus FLM formula has corrections at subleading orders in G Newton and so on. And we certainly, all of these are derived using the gravitational path integral, and there could be non-perturbative corrections of all sorts. So exact quantum error correction is often not the ideal situation. And so it was also shown that you could account for approximate error correction, which means that you have error correction up to some small errors. And still, the statement that there's an approximate equality between the bulk and boundary relative entropies is sufficient to show that there's a nice reconstruction map which reconstructs any given bulk operator in this blue region on the boundary subregion capital R. This is a non-trivial statement, and essentially it follows from the fact that the relative entropies being close is actually a very strong statement. The relative entropy is a very sensitive measure of distinguishability. So the fact that the relative entropies of these two states are close tells you that the states in many other measures are also close, and that's sufficient to prove that there's this property of subregion duality. So this is an important statement. However, as I said, this is a sufficient condition, but it's not a necessary condition. Okay, so what was assumed was if we have something like the JLMS formula, then we have a nice reconstruction map. But the converse is not necessarily true because, as I said, like the relative entropy is a very sensitive measure of distinguishability. So it could be that for all other reasonable measures of distinguishability, which allow you to reconstruct operators, the states are pretty close. But the relative entropies can be very different. And I'll give you some examples of that. So this is going to be an important point that this is a sufficient condition, but not a necessary condition. Okay, so good. So let me preview what this talk is going to be about. So the result that I want to highlight is the following. It's basically to say that one-sided modular flow is well approximated by what we call the kink transform, with some caveat that this kink transform is boundary condition preserving. What this means is the following. So what the kink transform is, it's a bulk, it's defined on the bulk side in the following way. Let's say I give you a Cauchy slice which passes through the extremal surface. So the boundaries are R and R bar. And this Cauchy slice includes gamma R. That's what I'm calling capital sigma. Then the kink transform is defined as follows. We consider a transformed initial data where we keep the induced metric the same. So the initial data in this context is the induced metric and the extrinsic curvature, right? So we keep the induced metric the same, but we add a delta function in the extrinsic curvature, which folds this Cauchy slice. So this Cauchy slice, this is roughly what you can think of as a one-sided boost, right? This is, I mean, it's not precisely a boost because there's not necessarily isometries in this spacetime, but it's roughly what you'd think of as a boost, right? So all it's doing is just taking this set of data to this set of data, which is a pretty simple transformation. And what I'm going to try to argue is that modular flow, one-sided modular flow, can be well approximated by this transformation. This doesn't, so here you could hand me some space-time, and then in order to get the new transformed space-time, I actually have to take this initial data and solve those equations of motion to figure out what it looks like everywhere. And that in general is a complicated problem. So this means that modular flow doesn't have a simple description in terms of the space-time transformation, but it does have a simple description in terms of the spatial slice. That has this simple description. Okay. All right. So the goal of this talk is going to be to derive this fact starting from first principles. So as I told you, what we know about modular flow in holography is from the JLMS formula. So we start with the JLMS formula and we consider some flow. So we need to consider an exponentiated version of this JLMS formula. And with that, we'll try to first argue that modular flow in certain contexts can be just approximated by the flow generated by the area in some approximation in terms of classical phase space. And then separately, we can prove that in the classical phase space, the HRT area flow generates this kink transform. So that's going to sort of complete the loop from starting from the JLMS formula all the way till this kink transform. Yes. 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 Yeah, this will be consistent with that. So okay, good. So your particular point will become important when we talk about this part of the talk, because I'm going to approximate the modular flow just by the area part of the flow, which won't have the property that you just said, because the area generates some kink, but then the singularities of that are cancelled out by the modular Hamiltonian. And there's going to be some caveats that I'll talk about in this context. So that's going to be important, but in general, it's going to be consistent. So that's a special case where the kink transform just doesn't change the spacetime. And it's all it does is just takes you from one Cauchy slice of the thermofield double to a different slice, which are related by symmetry, and so it's the same spacetime. So that's a very special example, but this is going to work for more general situations. Okay, good. So let me start with the JLMS formula. And what I'm going to start off is by saying that there were some caveats to what. Yes, yeah.
This kink transform, why do you want to do it? Like, what is the thing that you want to eventually calculate?
Oh, so you could imagine wanting to calculate things like correlators in the modular float state and things like that. So what I want is a holographic description of what the one-sided modular float state is. And then you hopefully use holography to compute things in that.
And these modular flows are of particular kind. You consider particular K row.
I will talk about that. Yeah. Good. Okay, so let me start with the JLMS formula. So when really does JLMS formula hold? So as I told you before, it was proved in those papers, but there were some caveats which weren't discussed, and so I'm going to mention all of those now. The ingredients that JLMS really needed was replica symmetry in the Euclidean path integral. So what they assumed, it's analogous to what Lukowitz and Maldacena assumed for the entropy. And there's a similar calculation you can do for the relative entropy, where you assume replica symmetry. In the recent years, since we've gotten more control over the path integral, this point has been called into question for various purposes. Firstly, when you're near so there are various situations where replica symmetry breaking saddles can actually be important. So one such example is when you're near an entanglement phase transition. So in some sense, the Ryuta-Kinagi formula is not well defined, or although we understand in what sense it holds in various models. And typically what happens is it leads to order 1 over square root g corrections, which are significantly large to the FLM formula. And there are also what are called these incompressible states. So these are states which often involve superpositions of different spacetimes. And in those contexts, there are actually order 1 over g corrections to the FLM or quantum extremal surface formula. So firstly, this is an important feature. So clearly, so already the JLMS formula should fail in these situations because replica symmetry is just not a good assumption. And roughly, so this is the assumption that was made in the context of the Euclidean path integral. The Lorentzian analog of that is roughly that instead of having an exact error correcting code where you have an exact map and an exact FLM formula, you have something like an approximate error correcting code. And in fact, recently, people have discussed black holes in this context where it's not even an approximately isometric code in the sense that the map from the bulk to the boundary is not necessarily approximately an isometry. In fact, it can map a large number of states in the black hole interior to a smaller number of states in the black hole, in the boundary Hilbert space. So accounting for these corrections is important, and that's sort of going to be the Lorentzian analog of the things that we're missing here. So, yeah. So the non-isometric thing is important there, because if it was an isometry, then you'd say that all of these states should be counted. But now the problem is those states look orthogonal on the bulk side, but they're not, or they map to states that aren't orthogonal on the boundary side. You shouldn't naively just add them up and count that as the black hole entropy. It's basically like so yeah, exactly. So bag of gold, you can add like arbitrarily many states. Yeah, so this is some subtlety about the semi-classical description. So it's like here we're starting with the semi-classical description and trying to map that. And it naively seems like the semi-classical description has too many states. With this bag of golds, often people would say these just aren't states. But this story is essentially trying to say you can still think of them as semi-classical holographic states, but with this caveat that there's some small overlaps between these states, which sort of drastically cuts down the size of this. Yeah. Uh-huh.
Those are probably not then minus S correction. That's actually that's probably almost orthogonal states being in higher.
Yes. Yeah.
Probably are bags of goods which probably are not in the those probably also exist. You could also have, in fact, islands are probably one example. Entangles are which is a mixed thing. So if you have something inside, it's actually described as a box. Take back. So you probably have both. You have the fact that there are states in the bulk that are pure orthogonal but are not orthogonal. There are also some states in the bulk that are not pure states. They just not described as orthogonal. For example, it's
yeah. Yeah.
It still looks like a black hole.
Yeah, but the problem is, so that's a specific state. Like, so let's say you have some modes in the interior, you're entangling them with this bath region, then there's an island. But within that subspace of states, there are states which are product states which don't have an island. And yeah, all I'm trying to say is if you look at that subspace of states, there's too many states, and many of them don't have an island. So they must be mapped to the boundary Hilbert space. Yeah. Yeah.
won't map to boundary states. They're mixed states. They're not pure
Okay, it's in a more generalized sense, I guess it maps the boundary plus the bath. And yeah, okay, fair enough. Yeah. Okay. So good. So as I said, so there are situations where there are large corrections to the quantum extremal surface formula and also the FLM formula. And those definitely imply JLMS corrections just because the same assumption of replica symmetry was made. And so clearly, if there's corrections to one, there's going to be corrections to the other. And this can be made pretty precise. But there's actually more. And this was something that was missed earlier. So that's the caveat that I want to talk about now. So the way the JLMS formula is derived is the following. So you perturb the FLM formula. So the FLM formula tells you what's the boundary entropy of any particular state reduced to the region capital R. Right? So now we consider two states, rho and rho plus delta rho. Taking the difference of these, you can expand in powers of delta rho. And the leading order term is basically the expectation of the modular Hamiltonian. It's the trace with delta rho. And in order to derive JLMS, what we do is typically just drop all the higher order terms. Once you do that, it's by considering arbitrary delta rho, you basically figure out what, you basically get an operator relation which relates the modular Hamiltonians. So it's important to drop all of these higher terms there. But these higher terms can be subtle in certain situations. So let's say you have an approximate error correcting code. Then you can't always neglect this term because it comes with inverse powers of the density matrix. And suppose this density matrix has sufficiently small eigenvalues. So if this has small eigenvalues, this term can be large. In the exact error correcting code story, you could always choose delta rho to be arbitrarily small, right? So you can always take the limit where delta rho is much smaller than anything else in the problem. And then you can always drop all of these higher terms. But in the approximate story, there's an error, right? So the FLM formula itself has an error. So you don't want this term to be lost in those errors. So you certainly need, there's a lower bound on how big a perturbation you need to consider. And once you take that into account, these small eigenvalues are a problem. So there are situations you can find in toy models like tensor networks and the JT gravity with end of the world brains, where this term actually becomes important, and this leads to large corrections to the JLMS formula. So the JLMS formula just fails, even though reconstruction doesn't fail. So this can be situations where there's an island and you're way past the page time, and so you can explicitly see that there's a map that can reconstruct the interior operators on your bath, but still you can check that the JLMS formula fails, right? So this is some subtlety that was missed earlier. And the fix is also a little straightforward. It's basically to restrict to states where this term is not important. So that's what we call log stable states. Log stable states will essentially have no very small eigenvalues, which is controlled by the errors in the FLM formula. And once you restrict to those class of states, you can apply this argument that was made earlier and get the JLMS relation. So with this caveat, we can recover the JLMS formula. So whatever I'm going to say is always going to be restricted to states of this form. This is often true of smooth quantum field theory states in the bulk, because they typically have thermal distributions and they have some nice smooth behavior. But in these toy models, you can consider things like product states, right? And they always have small eigenvalues. So good. So now that we have the JLMS formula in this nice class of states, we can think about exponentiating it. And there's already a subtlety at that level. So remember that what the kink transform does, so just to preempt that we're going to land at this point, the Cauchy slice has changed by a delta function that's local at this extremal surface. And just by causality, the two wedges that are associated with them don't change, right? So the wedges, the yellow wedge and the blue wedge, aren't affected by this transformation, but everything in the future and past is affected. So this is a completely different spacetime. And this is a context which is very different from the traditional error correction story. In the traditional error correction story, what you consider is one particular background and small perturbations on top of it. This is also what we usually do in QFT and curved spacetime, right? In this context, in order to derive anything of this form, we would need to include multiple background geometries where the area has different values, and so it has some non-trivial behavior in different spacetimes. So, moreover, it's actually non-trivial to exponentiate the JLMS formula. So, what we have is this form, which says that the projected modular Hamiltonian equals a over 4g plus the bulk modular Hamiltonian. But this only implies this exponentiated version where I exponentiate the modular Hamiltonian on both sides, only if the projectors actually commute with the modular Hamiltonian, right? I mean, you basically take powers of KR here, and you want to move PC past each other. This statement is actually equivalent, as it was shown in this paper, to saying that the gravitational sector has approximately flat spectrum. So the entropy on the boundary side is computed by two terms. There's a gravitational term, which is the area term, and there's some bulk term, right? Now, general states in holography, like for example, the vacuum state, do not have a flat spectrum, right? They have some non-trivial thermal spectrum. And so if you compute the Renyi entropies, there's a non-trivial behavior as a function of the Renyi index. And so if you want some property of this form, what you need to do is instead consider a different class of states, which are what was called fixed area states, where the spectrum is actually flat. So these are more like the microcanonical ensemble, where you don't have this thermal spectrum and you project onto some small window of states near the peak of the spectrum, so that the spectrum is approximately flat. Right? There's no large fluctuations, and so the Renyi spectrum just stays independent of a function of n. So we're going to use a code subspace that has these fixed area states, and we're going to take it for different values of the area. So we just build, so we have one background defined by one particular value of the area, and then we build many such states with many different values of the area and then patch them together. So that's sort of going to be the bulk Hilbert space that we're going to consider. And as I said before, we're always going to be using a UV cutoff in the bulk. So this is some approximation where each of these terms separately makes sense, and A over 4G is much larger than KR. And also I'm going to be assuming that there's some nice factorization. So we're going to consider some type 1 approximation. So there's been a lot of work recently by Witten and collaborators where they've worked in the continuum limit, and they've tried to take this, find this type 2 algebra in the gravitational side. This is going to be slightly complementary to that because we're going to work in this type 1 approximation because we're explicitly imposing, you can think of it as a brick wall cutoff or something at the Ryutakianagi surface. And so it's not going to be in the continuum limit. So it's slightly different from that story. Okay, good. So as I said before, we're going to need these fixed area states. So to be precise, we're first going to choose a small code subspace, which is a particular background defined by this fixed area state with some perturbative quantum field theory excitations. That's one background in our code subspace. And there's some technical caveat that we need to take the width of the state to be pretty small. It has to be smaller than order G Newton. This actually ensures that these fixed area states don't actually have a nice semi-classical space-time in the future and past. This is basically because if you fix the area too sharply, then the boost angle about that point is highly fluctuating. And so there's no nice future and past. So this is in some sense a singular basis, but this basis will include states which are smooth. So we're just using this as a technical tool to be able to access other states. These just give us the advantage that we can do things like exponentiate the JLMS formula. So it's almost a technical trick here. Yeah. Yes. Yeah, I'm not going to literally like, so good. Okay, so within any of these particular code subspaces, you can derive JLMS in the same way that it was derived originally. And then these different subspaces are going to be pretty orthogonal to each other. So you can basically just patch together these operators. Yeah. Yeah. Yes, that's true. And Yeah, so I was just going to say that that's true, and the point is going to be that the number of states that we're superposing is going to be small because we're just considering some small perturbative QFT excitations with a dimension which is order 1.
States are singular.
Yes. 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 Yeah, but that's what I'm saying. So each of these has just an order 1 number of bulk states, and I'm just going to patch them together, and they're orthogonal in like the gravitational approximation, right? Like, yes. It's exponentially many states on the boundary, but it's not exponentially many states in the bulk. On the boundary we do. I don't think I mean, those would be the micro states, right? Like what you're talking about is like if you had the actual description of the micro states, but here it's like I'm fixing this classical background and just considering some small set of excitations on top of that. That's a pretty small number of states. Yeah. Yeah, it's not order 1, it's like order 1 over square root g or something, but it's polynomial. Yeah, basically, like if I give you the vacuum of the CFT, you can approximate it with some set of states like that. Yeah. Essentially what we're doing, so if you think about it on the boundary side, we're like, there's some spectrum and each small window there has an exponentially large number of states. We're just projecting onto different windows and then adding them together. So the number of windows I'm projecting onto is just polynomial in G, even though each window itself has exponentially many states. Okay, good. So once we do that, then there's a theorem we can prove, which is an approximate version of FLM. How am I doing on time? Pretty bad. Okay. So there's an approximate version of FLM that we can assume for these log stable states, which I said was these nice class of states where you can derive the JLMS formula, and we get some sort of approximate version of the JLMS formula. And as I said, so what we're going to do is take many of these small code subspaces, patch them together to what we call the large code subspace. We build like a direct sum over all of these. And as long as they satisfy some orthogonality conditions, just some technical conditions I'm not going to go into, but the important point is the areas are different. So in the gravitational path integral approximation, these are just orthogonal. So there are going to be some small overlaps maybe, but we can assume that they're small. And then again, for a nice class of states, we get something like the JLMS formula, but now for this larger Hilbert space, which includes all of these different classical backgrounds. Yeah, so this norm it's the infinity norm is what's called the operator norm. The operator norm is basically the largest eigenvalue of this operator. So that basically means that these two operators differ at most by this much. That's yeah. So it's what's the traditional norm. It's if you want to check whether two operators are close, this is the right norm to check. Okay, and now for the exponentiated version of this, we need an imaginary Renyi version of the FLM formula. So the typical FLM formula that we consider is entropy equals A over 4G plus bulk entropy. To derive something like this, we need we have to assume a Renyi version of this, where we change the Renyi index by from 1 to 1 plus I lambda. And then using the fact that we had these fixed area states, it was easy to exponentiate things within the small code subspace and then patch them together. So in the end, we end up with this exponentiated version of JLMS, which again is basically saying that these two operators are close. So there's some other epsilon here. So you can approximate the action of this operator by the action of this operator, which is just the bulk action of the area operator plus the modular Hamiltonian. Yes.
So, like somewhat of maybe a big question. So let's say if I just I'm in the CFT. Right?
You're in the CFT.
And I don't know anything about the gravities.
Yeah.
Formula.
Yeah.
Now, why would I do this in the CFD?
Yeah, that's a good question. So this seems pretty convoluted from the perspective of the CFD. This is what the philosophy here is just, if I give you a nice CFD which has this bulk description, this gives you an extra tool to compute this modular flow. In general, this is not going to be useful at all. I mean, in general, I don't even expect anything of this form to hold. Like this, it's not going to have an error correcting problem.
Large N.
Just large N?
Large N CFD. Some large N.
Okay,
I do not know a priori whether it has a bulk description or not. Okay.
Got it.
But it's a large N, maybe even strongly coupled, let's say.
Okay.
If you want, you can even make it gap.
Yeah.
All these things, there is a reason to believe that these kind of things make sense in such a theory?
Yeah, I think so.
I just wanted to know, like, so is there some CFD way of thinking about these things that make?
Yeah, so the CFD way of, so good. So there's not a sharp way. I mean, in principle, there's some way in which you can represent all of these bulk objects on the boundary, but this is not something we understand very explicitly. But suppose you had access to this bulk boundary map, and you were some powerful quantum gravity person, then what is nice about these theories, large N strongly coupled theories, is that roughly all the states that we'll write down, or at least if they have this nice semi-classical part, will break into these two parts. One which is like the area, which behaves very classically, and then there's some quantum corrections on top of that. Even formally, like if I hand you like n equals 4 super Young mills, you could decompose the Hilbert space in something like this and look at the action of modular flow on those class of states. And they'll have this nice property just because they have this nice holographic dual. Now, whether that's something you can actually do on the CFD is more complicated, but yeah.
I mean, I'm not saying how do you explicitly do it, but
Yeah.
is there a reason to believe just formally on the CFD side that such a thing makes sense?
If you don't have a bulk flow, I don't see where it makes sense.
Yeah. Yeah, but I mean, but don't we, okay, when you say large N strongly coupled, I assume that you mean that we have a bulk dual. Yeah, I mean, this large gap is usually just large coupling, no? Maybe yeah, okay. Maybe we should just call it holographic theory. So, yeah, okay. Yeah.
E over 4G, I think I take any kind of yes,
Yeah. Yeah.
But it can probably be done also in some. If you get the bulk dual, it is fine. Right. That's what the company.
With stringy modes, let's say. I mean, yeah, you can do it. I mean, in the sense you need to interpret what the area operator is on the CFD. You write some operator which basically has these properties. Then, yeah, you can do it. It's only formally defined, right? Like, so all we needed was, we started with the FLM formula, right? So, sorry, it's not useful. We just needed something like this, right? So this is a well-defined thing on the boundary. And then all we need is find some operator which behaves roughly like this. And that's some decomposition of the CFD Hilbert space, which is probably complicated, but in principle, you could do it. Yeah. Most of these arguments have been in the context of holographic CFDs with which aren't very stringy bulk duals and so on. But maybe of late, as I was talking about slightly, this story by Witten and so forth, as it's maybe pointing to more generalized versions of this, because all they needed there was large N. Strong coupling doesn't really get used in that context for the algebraic thing. You can. I'm just saying that now you could worry that, so that's like with a UV cutoff, but then you could say, oh, but what happens in the continuum limit? Like, is there anything of this sort? And naively, I would have thought once you go away from strong coupling, you just have nothing like this nice algebra. But it seems like even at finite coupling, you have something of that sort. That's, I think, non-trivial. I mean, I think it's pointing in some direction. And it's plausible that some of these ideas go beyond just classical gravity, semi-classical gravity. That's just a heuristic comment. Yeah. Okay. Okay, good. So good. So once we assume this, then we get this exponentiated version of the JLMS formula. So now we have all the ingredients that we need to understand modular flow in semi-classical spacetimes. So let's get to that point. And the idea is going to be now to approximate modular flow by the area flow. I'm going to be precise about in what sense that's true. So firstly, naively, so there's a statement that the entropy of the boundary is approximately given by the area A over 4G, right? The bulk corrections are typically order 1 and they're small. So naively, you might think the modular Hamiltonian is also just approximately the area operator, and the bulk modular Hamiltonian just doesn't matter. You can just drop that and then we're done. But that's actually not true in this large code subspace. So let's take a simple example. Just consider BTZ black holes of different areas. So that's a simple version of this code subspace where I just take one background of one BTZ black hole and then patch it together with other BTZ black holes of different areas. The modular Hamiltonian in the thermal state is something we understand well, right? So we can write down the modular Hamiltonian independently, and just using gravity, it's related to the area operator in this form. So it's basically given, it's quadratic in the area operator. This is just coming from the fact, this is just by relating the ADM energy to the area. And so we can write this suggestively as A over 4G plus some piece, which looks like it's quadratic in A, but it's peaked at the right value. So the interpretation of this is the modular Hamiltonian is basically the log of the density matrix, right? So in the thermal state, there's some thermal spectrum of which is the distribution over these different backgrounds. So there's a peak background, which is the classical background that we typically work with, but there's some exponentially small amplitudes of being in any of these other backgrounds. So there's an exponentially decaying probability, but when we take minus of the log, that's a quadratically growing amplitude.
Understand this statement.
Yes.
Hat pair by area.
A hat is the area, yeah.
Then you have area in the denominator also.
Oh, this A beta is, okay, good. So let me be more precise about that. So let's say I give you the state e to the minus beta h for a specific beta, right? Now that will have some peak value of the area. That's like the classical background that you'd work with at that particular temperature. That area is A beta. And now I'm interpreting this as an operator that acts on this Hilbert space. So the Hilbert space is labeled by different values of the area or equivalently labeled by different values of the energy, right? In this special context of BTZ black holes. At the classical level, there's some simple relation between them. So all I'm doing is this side is just beta times h, which is the ADM energy, and I'm just writing that in terms of the area.
Why do you get the area in the denominator?
Oh, I mean, this is just a calculation. Like this just comes from just computing this in the bulk. This is just suggestive. Like really what you'll get is some factors of, I don't know, mass or whatever, like the peak value. It'll be some function of beta. I'm just writing it suggestively as A times beta, as A of beta.
Why isn't it just A hat by 4G?
Yeah, that's the thing I'm trying to tell you. So good. So the energy in so instead of labeling everything by A, let me label everything by the horizon radius, right? R plus. Then the area is 2 pi R plus, it's linear in R plus, but the energy is quadratic in R plus. And that's basically this relation. So this is just a suggestive rewriting of that fact. All I'm doing is just looking at the background, evaluating the area, and relating it to the energy. It's A over 4, so that's an important point. So let's say I was at A equals A beta, then this term drops out. And so there's a sense in which A over 4G is a good approximation near the peak of the spectrum. And that's what we typically use in thermodynamics, right? Like, so when we're evaluating the entropy, what we really care about is the peak of the spectrum. And there, the entropy will be approximately the area. So when we're taking an expectation value of this operator, this term will basically drop out. But as an operator, it's not close to A/4G. It has these large corrections.
Can you just understand this as, so I have like a thermodynamic state,
Yes,
but some canonical ensemble.
yes, yes.
And then you want to write down an operator which will give you the correct energy in thermal states and nearby perturbations.
In this context, let's just take exactly thermal states of different temperatures. Or different, we can also take like different energy windows, let's say.
Okay, so let's say thermal states of different temperatures.
Yeah.
How do you think about it? There's a code subspace for each temperature.
So there's a, so good. So you should think of each of each of the states as states which are microcanonical states of a particular energy window. And the thermal state is just a superposition over them, right? It's just with some enveloping function, which is a thermal distribution. So the Hilbert space is labeled by just those energy windows. So that's the set of states I'm looking at.
Code spaces for different energy windows.
Yeah, so those are my what I call small code subspace, which is this. And I'm taking the trivial case, but forget about bulk excitations altogether. It's just the classical background, and then patch them together into this large code subspace.
So now you want to make a large code subspace which is just made of thermal states at different.
So let's say energy, so microcanonical states of energy windows.
Yeah.
Microcanonical. Yeah.
Windows at this thing. Okay.
Yes.
And then your claim is that this is an operator.
Yeah.
Which gives you the correct energy.
Yeah.
In what?
So the operator, all it does is it goes to that particular energy, looks at the background and evaluates the area, right? So this A hat operator, that's what it does.
Yes.
And there's also an energy operator, which will just go to that and evaluate the energy. Now, just using classical gravity, we're just saying, oh, you could equivalently label everything by the radius or whatever. And the relation between these operators is just that it's the energy is quadratic in the area. That's this statement.
Yeah, it's just that, like from the CFT point of view, this is very weird because this is equivalent to trying to define an entropy operator. And
yeah, it's kind of like that, but it's not exactly like that, I think, because
I mean, it's like taking ideal gas and saying you say pressure P hat is equal to some N hat.
Yeah, that's right. So it's roughly like that. I think in this case, it just has a different interpretation because this area has this bulk interpretation separately. And so it kind of makes sense to think of this as an operator. Also in this statement, I was ignoring these bulk corrections because in general, the energy and area will not be related trivially, right? So the energy will be like area plus whatever bulk energy you have. There'll be some relation like that. So in this context, like this area operator is just, if you included bulk corrections, you'd subtract out whatever is the energy of the QFT part, and then you get the area. So it's some non-trivial operator, which is not exactly equal to the entropy operator that we think of.
Yeah. Could you just repeat? So let's say this is the operator. What were you saying?
Oh, sorry. So what I was saying was, so here the states were just like small windows of energies. And there was some probability distribution, which was peaked at some particular value in the thermal state, but then it has Gaussian fall-offs away from that. So the probability goes like e to the minus this term, right? And so when I take the log of the density matrix, I just get something of this form. So it's quadratically growing away because of these exponentially damped tails. And those exponentially damped tails become important in the operator. So if I was to take the modular Hamiltonian I obtained at one particular temperature and apply it to the modular Hamiltonian to the state, which is a different temperature, then these large corrections are important. That's the point. This is not, yeah, I've not seen any situation where people have considered this in holography, so it's a little unfamiliar, but that's the statement. And this is where I was, so initially there were these two states, right? So we had these rho and psi, and naively you could take them to be different. If you take them to be different, then you have to account for things like these corrections. If you take them to be the same, then you don't have to worry about it because evaluated on the state, the initial state you started with, this will just drop out because you're just evaluating at the peak of the spectrum.
Yeah, just that it's not very intuitively clear to me that the approximation which goes into writing down that formula, okay,
this one?
allows you to take a log and, like
out
of it.
Yeah, so this is, yeah, you could worry about that. This is all derived using the gravitational path integral. So this is all in the gravitational path integral approximation. Like you can basically compute the amplitude, the amplitude of something of the thermal state to be in a particular energy window, right? That's something we can compute. As you say, like there could be corrections to that from in the actual theory, which the gravitational path integral hasn't captured. That, yeah, I agree that gets missed here. But yeah, I mean, okay. Maybe one way to say it is like, maybe this is not under control, but it's just pointing out that there could be large corrections. Maybe that's one way to say it. So certainly you have to restrict to states where these extra terms drop out. Yeah. Okay. So good. So this also gives us the fix, which is basically when we're acting on a state which has the same background geometry, this term is small. And so we can now approximate the modular Hamiltonian with just the area operator. Okay. So that's the story here. So you can then do this approximation and basically check that the modular flow is well approximated by the area flow. Now, what that means is just that the background geometry agrees. So we're replacing the action of the modular Hamiltonian with the area part, which is just the gravitational part of the modular Hamiltonian, whereas there's also these QFT part of the modular Hamiltonian, right? So that we're dropping, which means that the quantum states are actually very different because as you were pointing out earlier, like the quantum states require, so the quantum state, when you actually perform this modular flow, will change by the bulk modular flow. And that's something we're ignoring. But that's okay at the level of the background geometry. So this statement of the kink transform here is just at the level of the background geometry. We can include quantum corrections separately, but at this point, that's the statement. So for example, if you look at two-sided correlation functions, so if you compute correlation functions on these two wedges, the area operator is something that commutes with both of them. It's space-like separated to either of these. Right? So the two-sided correlation functions don't change because the density matrix of these operators doesn't change. On the other hand, the vacuum at the horizon, which was Suvrat's comment, is destroyed by this area flow because what's smooth is the sum over A over. So this A over 4G creates this kink, and that's destroying the vacuum because you've destroyed the Minkowski structure of the vacuum near the RT surface. And usually the story is that that's regulated by the action of the bulk modular flow. In this context, if we approximate it just by the area flow, it is singular. It's, of course, regulated by the UV cutoff. So it's not infinite energy, but it's a large amount of energy. But that wouldn't happen for the modular flow. So with these caveats, what basically we're saying is that at the level of the classical background geometry, we can make this approximation. And then quantum corrections have to be introduced separately to account for what the quantum state is under this deformation. Okay. Good. So finally, let me come to the last part where we prove that, yeah. It's not smooth, so this background geometry actually will have shocks, but they're delta function shocks. I think so. I mean, these are still solutions to Einstein's equation. So let's say you forget about quantum field theory altogether, and I just hand you some classical state. This. Yeah. But at some subleading order. That's the thing. So the amount of energy is regulated by this UV cutoff, which we're taking to be much below the Planck scale. So the corrections will be controlled by this UV cutoff. They'll be much smaller than the Planck scale. Yeah, so that was this previous part where I was trying to argue that that's not always true. This is true sometimes, but with these caveats. But yeah. It does. It's just not related to the modular Hamiltonian linearly. Yes, but I'm just saying that the action of the modular Hamiltonian is quadratic in the area, so you can't just approximate the modular flow by the flow by this A/4G generically. That's what I was saying. So if you took the modular Hamiltonian you obtained at one temperature and applied it to a different temperature, then this term is important. And in that sense, to a different temperature. Sort of, yeah. That doesn't work. This was basically to point out this is the caveat. Like roughly what you said is correct. And that's correct when you're applying the modular Hamiltonian you got from a state on that same state. And
Nearby state.
sorry?
Or nearby state.
Or nearby states. And yeah. So finally, what we need to argue is that the area flow generates this kink. This is something that has been hinted at in the literature in various contexts. But we didn't find anything that was perfectly convincing, especially because very often the importance of extremality is ignored. Like it's very important here that we're considering the HRT operator, which is an extremal surface. And mostly classical phase space analysis considers situations where you have a one-sided phase space with a boundary at one end. But in this context, we really wanted a two-sided phase space where we have these two wedges that are glued together, and we want to consider the phase space of that. So in that context, what we want to do is now consider the flow of any observable. So let's consider any observable O under this flow, which is generated by the bracket with A/4G. So this is just the classical analog of the flow equation for the modular flow once we've approximated it by the area flow. And in order to compute this, you essentially can use this Peierls bracket technique that was talked about in this paper. When you do that, what you do is essentially start with the action that you had, which is the Einstein action, deform the action with the operator that you want to compute the bracket for. So in this context, we'll consider A/4G, and you add a source, which is represented by this red dot here, which is sourced by the area. But now it's important that it's the area of an extremal surface. It's not the area of some surface that is dressed to the boundary with some distance or so on, because the source that's generated by any such area would include some non-local pieces. The area being extremal makes it a local source at the extremal surface. That's sort of an important point.
By turning on a source with the area and so on, you're just saying there's some kind of an object which has a tension?
Yeah, you can think of it as it'll basically be like having a cosmic brain with some tension. Which is small, like some perturbative tension. Yeah, exactly. So that's going to be exactly. So in that context, what you do is, so for the Peierls bracket in general, what you do is add this source, compute what's called the retarded solution, so the configuration where you hold the past fixed and consider the full solution. Similarly, you can consider the advanced solution, where you hold the future fixed and consider the full solution with this source. And then you take the difference between these. That's sort of the analog of like the Feynman solution, roughly. It's like retarded minus advanced. And that's a linearized solution of the original theory. So this thing will, this Peierls solution will be a linearized solution of the original Einstein equations without any source. So the source sort of cancels at linear order when you take the difference of these two. And so in order to compute this bracket, what you do is look at the observable in this solution and compare it with the original solution. The difference that you get is basically the bracket. And this is like some linear response picture. So
that's not like Feynman solution. In Feynman solution, the curve doesn't cancel
out. Yeah, sorry. So maybe you shouldn't call it that. Yeah, I only meant in terms of it's like some linear combination of retarded and advanced, but yeah, it's not. The source doesn't cancel. Yeah, in this context, the source cancels.
Like this Dirac's prescription where you calculate advanced minus retarded, which you use to the regular solution to calculate the radiation reaction. Which is regular at the source because it's a homogeneous solution of the.
So you're saying it is that?
Seems more.
Yeah. I think that's probably true. Yeah.
So this is a solution which is completely regular at the source. Right?
Yes. Yeah, it's a solution to the unsourced equations of motion. So it's some sort of linear response type picture. In that sense, it's kind of like computing a Green's function. But it is a solution to the original equations of motion. And what you do is now just compute. Yeah. So did you say something? Okay. So you compute the value of the observable in this solution and take the difference from here. That's basically the interpretation of this is basically how does the observable O respond to adding a source A over 4G in this particular way. And that's sort of the linear response interpretation of this bracket. So when you do that, as was pointing out before, the addition of this A over 4G essentially creates, it's like adding a brain, but it's basically in Lorentzian signature. So what it does, it creates a Lorentzian conical defect. So what the solution looks like for the following, there's a Cauchy slice just below the cone, and there's a kink slice just above it. The solution is of this form. Now, using this, it's sort of straightforward to read out the kink transformation. So here we want to look at the flow equation for the data on a particular Cauchy slice. So we just look at the effect on the initial data. As we can see from here, there's continuity in the induced metric, so that doesn't change. Hij stays Hij, but there's a kink in the extrinsic curvature, and that picks up a delta function, with some coefficient that's fixed by the coefficient of the area operator that we added to the action at linearized level. So we get this effect, and this is precisely what the kink is after we integrate it, so to finite values of k. And so that's sort of a derivation of what I claimed. There's an analogous result you can derive by using Poisson brackets. I like this much more because it's sort of a gauge invariant way of seeing things, but it's equivalent to this result. Okay, so I had some comments on higher derivative theories, which I'll just briefly mention. The story is often that, so in the Euclidean context, what's known is that the area over 4G gets promoted to what's called sigma, the geometric entropy, which includes the walled entropy and some higher extrinsic curvature corrections when we compute the entropy in higher derivative theories. And in general, the action is singular for these conical spacetimes. So you really need to provide, it's difficult to go through the same process because once you add in a source which is a cone, there's a delta function, and if you have these higher order terms, then there's going to be singularities in it. So you need to know how to regulate it. There was some prescription that was made in this paper by Dong and Marolf, where they defined a different action, which is the action outside the conical defect with some counter terms which absorb some divergences. And they showed that this was a good variational principle for fixed values of the conical defect. So remember that here what we were doing was we had some fixed value, there was some, we added a source of this area, and this is some analog of that, where we just solve for the variational principle with the original boundary conditions plus the existence of a conical defect in the space-time. Once you solve for that, they showed that this action is good. It satisfies a good variation principle, and that the derivative with respect to this conical defect is the geometric entropy. So this is a reformulation of how Dong derived the geometric entropy. And once you do that, now everything is finite, so you can define the action by including stuff inside the conical defect by just adding in this extra term. It's just like a Legendre transform. I'm happy to talk about this later. Maybe it's should end. So what we've been trying to do is try to do this analogous calculation in higher derivative theories. We've already checked it in some simple dilaton examples. And it's basically a generalization of the kink transform, where you again add in a Lorentzian kink, a Lorentzian cone, and compare the data before and after that. So going back to what we were saying before, so this is sort of a singular solution, right? So this one-sided modular flow is a singular operation on the side of the quantum field theory, on the boundary quantum field theory, but you can regularize it. So one way to regularize it is what's called the Kohn-Cocycle flow. So instead of considering the flow that was just the modular flow, which is just this term, now let's say we take the state psi, get some density matrix K, flow by e to the minus k lambda, but then we reverse flow by the vacuum modular Hamiltonian. Now, the vacuum modular Hamiltonian in some situations is a nice thing that we have control over. So for example, if I take half space of a quantum field theory, then the vacuum modular Hamiltonian is just a symmetry transformation, right? So once on the boundary, it's just generating a boost. And so that on the bulk side, all it does is just a diffeomorphism that moves the boundary by a boost. So essentially, the state that's this concocycle flowed state is related to the modular flowed state by just some singular diffeomorphism. And now this is a smooth state, smooth up to some delta function shocks on the light cones. And there's a precision test that we can do for this, which was done in this paper, which is there's a stress tensor shock on the boundary. So there's a delta function in the stress tensor in this concocycle flowed state that was known independently just from quantum field theory considerations. And we can check that if you look at the near boundary region of the RT surface, you can match it to a Weyl shock in the bulk. So there's a Weyl tensor shock along the light cones, which matches precisely with the stress tensor shock on the boundary. So that's some evidence for all of this being true. So let me just summarize. So what I tried to do is go from the JLMS formula to prove that the modular flow is given by a kink transform. On the way, we saw that there are corrections to the JLMS formula when we consider approximate error correcting codes, and we had to restrict to what we call log stable states, which was this nice class of states. Then we considered this exponentiated version of the JLMS formula, which used a large code subspace of many different background geometries that was built out of these fixed area states. We then approximated the modular flow with area flow and showed that in general, there are corrections from this from the bulk term in semi-classical states. And so we had to be careful to apply the modular Hamiltonian on a nearby state. And finally, we've showed that the area flow is also approximated by the kink transform, which we used the Peierls bracket for. So hopefully that convinces you that modular flow in holography is well approximated by this kink transform. So with that, let me thank you.
Are there more questions for Pratik?
Maybe could you say a bit more about this mapping between this stress tensor shock and the Weyl shock?
Yeah, so here what we were doing was we were considering a general situation where some arbitrary metric in the bulk, which just has some nice ADS asymptotic. So it has some Pfefferman-Graham expansion near the entangling surface. So the stress tensor shock was known from the boundary side. And what it does is the shock is proportional to the entropy derivative. So there's a delta function at the location of the entangling surface, which is proportional to this flow. So it's proportional to the flow parameter. Firstly, you need to flow for it, but it's proportional. The coefficient in front is the entropy derivative at that point. Now, when you look at the bulk side, and you just look at the near boundary region, the stress tensor is related to the Weyl tensor in the boundary side. And essentially what you do is look at the shape of the RT surface near the boundary. So if you write that down in a Pfefferman-Graham expansion, there's a term in that which is proportional to the entropy derivative, which maps to the entropy derivative. And it turns out to be related to the shear on the surface. So when you do this kink transform, the constraint equations of Einstein equations are the constraint equations are satisfied because of extremality. So it's important that you can add in this kink only at the location that's extremal. But if there's a non-zero shear, then you have to sources a Weyl shock which balances the other equation, which has the shear in it. So just abstractly from the kink side, you can show that if you have a non-zero shear, you have a Weyl shock that supports it. On the boundary side, we know that if you have an entropy derivative, then you have a stress tensor shock. And by working near the boundary, you can check that these two agree with each other.
And this is a statement in general D.
This is this is the it's slightly more complicated in 3 dimensions. Like this, it's much easier to say in this way. There's no wild tensor there, but there it turns out to be related to the shape of the boundary. Like it's the boundary graviton essentially. But you can match it even there, like just by working in this near boundary region.
Can I just ask one more question?
Yeah.
In the sense that, let's say, like, I mean, how is this statement related to the statement of, let's say, something like first law and so on? That if you change
First law.
So there are these statements like, if you change the entanglement surface, deform it by something. Then how does it change various things in the bulk, and how does it relate to Einstein equations and so on?
You mean under a state deformation?
No, under just a surface deformation.
Surface deformation.
Let's say. Like you can also probably do a state deformation. You can just put some either one. Should I understand it, this statement as somehow similar to that statement? Is there some
I mean, I guess you could consider like this is some state deformation, right? And you could probably apply at linearized level, just look at the operator that's generating that state and think of that as a state deformation. And the expectation value of the stress tensor there picks up some delta function. And maybe in that context, you can think about it that. It's a special case of that, maybe.
And so on and so forth. Actually, the deformations you can, because the modular Hamiltonian is just integral of the stress tensor. Right?
So this k omega is simple because it's just the integrated stress tensor. This k rho in general is the complicated thing, and that's the thing. I mean, in principle you can, but we don't have any control over that calculation. That's the subtle thing, I think. So this holography is helping you attack that part. In principle, you could compute it from both sides, but it's hard. The k omega part is simple, as you said.
Any further questions? Are there any questions from the audience online? Feel free to unmute and ask. Okay, I hear nothing, so let's thank Pratik again.
Thank you.